Hi, everybody. Thank you for joining us today for Semi-Rigid Diaphragms. My name is Debbie Penko, and let's get started. So just kind of start out a little bit here. We're just going to talk about what the topic is we're going to be discussing today, give you a little overview. The first thing we want to talk about is what the lateral load path is and why we're even talking about diaphragm. So we'll start out with kind of the idea of what the diaphragm is. We'll go through some of the diaphragm behavior. Today we'll be talking about semi-rigid diaphragms in focus, but it is important to understand what a rigid diaphragm is, as well as a flexible diaphragm, in order to understand why you might want to use a semi-rigid diaphragm. I will also talk about how these diaphragms get used in Risa. There's different levels of automation in the Risa products. So we'll focus today on Risa Floor and Risa 3D, those two programs, and how they use the diaphragms. And then we will also get into some modeling examples. So this presentation is a little bit heavier in PowerPoint, but we will jump right into the models and understand how that would get used in your model. So starting out with that load path, we're talking here about lateral loads, and what we're talking about with diaphragms is how we distribute lateral loads. In this example here, I've got a wind example, and if we see here in this diagram here, I'm applying a wind to the walls and to the roof, and what's resisting that wind on that building is the diaphragm. It's going to be going here in the in plane of that diaphragm. That transfers to our lateral resisting system, which then carries the loads down to our foundation. So really what we're at the goal here is to design your lateral resisting system, whether that be shear walls or brace frames or moment frames or whatever it happens to be. You're carrying those loads through that diaphragm and into those lateral resisting elements and then down to the foundation. So what is that diaphragm and what kind of diaphragm do you want to be using? So the diaphragm represents here in this case the floor level. It can be the roof, it can be the floor, it can be however what it happens to be, but it's going to be distributing those loads. So looking at this in a plan view, we're looking down on this model now. We're thinking about these as shear walls. We'll just kind of simplify this to a simple 3-wall example. Shear walls here on the outer edges and in the middle, and the diaphragm is just kind of going around the edge there. So assuming it's a typical floor model here that we're just looking at one floor level. The wind and the seismic would be applied maybe as a uniform load to this diaphragm. We'll see how there's different methods to apply that load for each type of wind or seismic, but just in simplicity, we'll talk about this applied as a uniform load. Now, what we're trying to do is saying we're transferring the loads to those shear walls. So if we, first of all, call this a rigid diaphragm, then what we would be doing is we would be carrying this load directly to those shear walls rigidly, which means equally distributed. So we're seeing here that if we had 3 shear walls, those 3 shear walls will each receive the same exact amount of shear into them. So we would say that would be W would be our representation of our wind load, and that would be applied into it as a divided by 3 into each wall. So that's a concept that would mean that each one is going to be receiving the exact same amount of load, but that's only considered if that diaphragm is fully rigid. So the diaphragm sends all that load through, the load goes into the diaphragm, into the shear walls, but it's considered that that's fully rigid, so it distributes directly to each one based on the rigidity of that element. So I'm assuming here that this wall is equal in all 3 walls. Its length and its stiffness is equal. And so then I see the load get directly into that. Now you'll also notice my deflected shape of that. It's sort of a rigid, idealistic idea of the fact that this is completely rigid. Internally, the thought is that you're basically tying all of this with rigid elements under the hood of the structural model, where you're applying that load, and it's going to be using those rigid links to tie every single element together. And as you apply the load, it gets distributed into that model. So this is kind of a common topic, a common way to model lateral systems, and we'll see that coming forward here. We'll use some rigid diaphragms as well. The second method here is to use flexible diaphragms. And in a flexible diaphragm, really that's just no diaphragm. Flexible means it's completely flexible. There is no resistance. There's no stiffness. So when you look at this model here, what I've done here is I've applied that load, and the diaphragm just got out of the way because it was completely flexible. So it distributed loads to the walls based on their tributary area. So you can see on the outer walls there, you're getting a quarter of the load because it's going to be seeing a tributary area of a quarter of that, or half the span between the next wall. And then the middle wall is going to be seeing half the load. And that's a fully flexible diaphragm. So this is kind of also a little idealistic because you're saying all of the load is going to be going directly to those elements. This is really good for hand calc methods because it's easy for you to make that tributary area method. But it is saying that there is just zero stiffness in the model for that diaphragm. So the first one says it's fully stiff. The second one says it's zero stiffness. And then the nice one on the third option, which what we're focusing on today, is semi-rigid. So in this case, we're actually drawing in the diaphragm using plate elements. And as we apply that load, we can see the load gets dragged through the diaphragm. So we see the loads, that plate, you can see I meshed those plates and you can see them deflecting. And that deflection is carrying those loads, and there's going to be some forces and stresses in those plates that helps distribute the loads to the wall elements. So you're going to see roughly the type of load. It looks like I have a little misprint here. It's going to be about a quarter to a third of the loads on the outside wall elements, about a half to a third of the loads there directly to the middle element there. But what you're seeing is going to be, it's based on the stiffness of that diaphragm. So a little bit more like reality, although one thing to consider as we start this semi-rigid diaphragm topic is you can see one thing that the other two did not have. We have a lot more elements in our model. So we put plate elements throughout this, which means now there's more complexity to the model. It's a larger model. We've now have, as however many plates are shown here, we have that as well as the wall elements that are also plated. So it becomes a bigger model, just inherently. More accurate possibly, but also that accuracy, you're going to maybe lose in speed or modeling time, things like that. So you have to consider what you need for each one. The code is interesting because you'll see different parts in the code where you can jump between rigid and flexible. I think the code recognizes that those are really time savers. And then there's times when you do need to get to the semi-rigid diaphragm level to get that accuracy. So you could, per different material, it depends. You can refer to the codes to see exactly when you need to do that. I'll be focusing on how to do it today. So if we kind of jump to the next slide here, kind of talk about Risa and how Risa apply these loads. So first topic would be Reso Floor and Risa 3D together. If you're not familiar with Reso Floor, so we'll focus on both programs, but Reso Floor, starting out, in Reso Floor, the traditional way you do modeling is to design the gravity loads in Reso Floor. So all the gravity system, the columns, the beams, it's going to carry all those loads vertically down the structure and design those elements. And then the program will calculate the lateral loads, and you'll carry only the lateral elements over to Risa 3D. So you're going to be taking your shear walls, your brace frames, things like that, and carrying it over into Risa 3D. There's an automatic load generation for you. We'll go into that here shortly, but you'll see that you can enter in the parameters, and you'll get the calculations of those lateral loads. And then you'll jump into Risa 3D, and Risa 3D will apply those lateral loads to your structure. So there's varying levels of automation for different types of structures. So for a semi-rigid diaphragm, you can automate the concrete floor level. If you want to use a flexible diaphragm, you can do that for a beam-supported floor level. And if you want to use rigid, you have the option for both the beam-supported and the concrete floor. So you have different automation levels for different diaphragms. So that's your Reso Floor and your Reso 3D together. Risa 3D by itself, we can do the same type of thing with just the rigid diaphragm. So that one is automated as well if you're using Risa 3D. We'll see here how to do that as a semi-rigid using a non-automated method. I'm going to see here a little bit about the automation of the lateral loads. So no matter what type of diaphragm you're using, you're always going to see this same screen for seismic loads. And what it does is at the top there, you can see it gives you the ability to set your code, set your parameters. The code will be calculating automatically the period for you using the hand calc methods. If you want to override that, you can. You're going to put the R factors in. You go ahead and put your SD1, SDS, S1. Those are going to be site parameters. So you take a look at your site and enter those in. And then really the power of this is going to be those forces in the X and forces in the Z direction. So you'll see there's a lot of different calculations in this sheet, But what we get out of this is those two values, they're applied in per floor level. So if we had this one, just an example of one floor, and we're going to see that that's going to go right into the force in the X and the force in the Z direction. And so no matter what type of diaphragm you're using, you're going to get this sheet. You'll also get the same sheet for wind loads. So wind loads you do very similarly. You plug in the wind speed, the exposure category. If you have any topographic effects there, you can apply those factors in there, and then it's going to generate those wind loads for you. And that same X and Z direction are going to be shown there. So basically per floor level, we're going to get that force value for that one level there. So we jump back in here, we'll talk more about how we apply that load to the program. If we just look at a simple floor plan for a rigid diaphragm, I'm looking at a floor plan, so a plan view, vertically that one force I mentioned here, the X direction, for example, here, if we're applying an X direction load, we're going to see that it just gets dropped right into the center of the model. Now that means that that rigid diaphragm is what carries it to the lateral resisting elements. So it's not like it's going to be just in space, it's actually tied to the diaphragm. And see that purple line here on the lower level, it's tied into that diaphragm. So in behind the scenes, Risa's doing is it's taking that and putting rigid links from that one point load to the elements that it's going to be considering the lateral elements. So it's going to the walls. If this here, I'm just going to say these would be cantilever columns here for this concrete system. Whatever it happens to be, those are going to be dropped into that structure if this was a rigid element, a rigid diaphragm. You don't ever see these rigid links. This is just theoretical behind the scenes. That's what the program is doing. If we jump to a flexible diaphragm, similarly, those same X and Z direction loads there are dropped in as a point load. So you can see here, this is a Z direction, this is going to be your X direction, just one point load. Now, as I mentioned, with a flexible diaphragm, you don't have the luxury to have that rigidity in there. All you're doing is taking that one point load. So what happens on the program when the model is run, it gets distributed to those elements based on their direction. So if we think about this here in the Z direction, if we apply the loads in that Z direction or horizontally across the screen, then it says, okay, the tributary area of all those walls that are going in that direction going to resist that load. That's where we're going to transfer that load to using that transient distributed load. So this is post-solution. You'll see that's for your representation of what happened in the model. That's how that point load got transferred to the structure. So it's really easy for you to verify what loads got transferred into the model. Same thing happens in the X direction. So if we put a load in that one direction in the X direction, we see it gets attributed to the walls in that direction that would be resisting that load. What's nice, if you notice, there are walls that are diagonal, and so those diagonal walls in both of these models here are getting slight loading because they have an element that is partially in the X direction and partially in the Z direction, right? So they're getting a little bit of that load in that direction as they are contributing to that direction. Might be a little harder if you're doing that by hand to try to get all those numbers, but this is all automated for you when you use a flexible diaphragm using Reso Floor, Reso Floor and Risa 3D together. Those two do a flexible diaphragm. I modeled here like a wood structure. That would be very common here for a flexible diaphragm. You might consider a steel, but typically a wood, we know a lot of times you might hit that as a flexible diaphragm. I'm going to jump here to semi-rigid. That's what we want to focus on here today is semi-rigid diaphragms. And semi-rigid diaphragms work similarly, but when I mentioned that, we had all those plate elements there. So when you see you're actually looking at your model, instead of having a zero diaphragm like a flexible diaphragm or a fully rigid, what happens is it gets submeshed into little plates all along that, meshed to all the control points that are important for that. So you can see that it's going to be meshed directly to the column tops or meshed directly to the walls. And that wind load gets applied as a load across there, a distributed load across the diaphragm. So there's a windward and a leeward force that goes directly onto that diaphragm. And you'll notice the numbers are a little different from the windward versus the leeward. So it's calculating all that value inside of there. And it's applying it into a WL plus X. So it's going to be a special semi-rigid basic load case called WL plus X. Now, since wind is a little different than seismic here, we'll see we do it in one direction because of the windward leeward. Then you also do it in the negative direction, and then the loads are slightly different from that. So you're going to see if it comes in, the wind comes from the other side, the values are going to flip-flop, and you're going to see the loads come in here from a little higher on the windward versus the leeward side on this example. So you've got that kind of looking at, you see that it comes from both sides going into the WL plus X and minus X. You're also going to see the same thing on the Z direction. So you're going to see you have it on the same, the windward and the leeward sides coming in for the wind loads. And it goes right into the diaphragm. Now the diaphragm load it's going to be distributed through those plates to those elements. So based on the stiffness of the diaphragm, that's how it gets distributed into the structure. So you'll see that we'll look at how that contours work inside of that model. We'll understand a little bit better about how we're actually distributing those loads. That's how wind is handled. Seismic is handled a slightly different way. So seismic has, what we do is we're taking actually all of the mass, the dynamic mass in the structure, and we're taking that dynamic mass and we're turning on its side to go in the X or the Z directions, and we're multiplying that by the factors here in the seismic code that we've calculated to determine how much of that mass vertical needs to go lateral. So you'll see kind of what happens is that you get a little bit of a column load, whatever's contributing to that in the column elements. You'll see the walls have got some point loads there and some line loads. And then the slab itself has a little bit of mass there, so that mass is going into that direction. So you've got all those, whatever's considered a dynamic mass needs to be going in a lateral direction. So there's more point loads and more surface loads than we'll see in an earthquake situation. Now, this is all going into an ELX load, and then to be able to reverse it, since it's equal, you can just use a negative factor on that, and it will just turn itself directionally the other way, a little less complicated than wind. So ELX and ELZ are just going to be a positive ELX and a positive ELZ, and then the next combination here to show it in the opposite direction would be showing it in a negative factor, so -1, and we'll see how that works in our load combinations. So earthquake, when you're doing your load combinations, is pretty simple, because you can just reverse the sign and see them go in 2 directions. So if we jump here to that same concept here, you'll see that when you're using Reso Floor with Risa 3D, that it will automate that for you. It puts the point loads directly into there. So it puts the point loads and for the earthquake ELX, it puts the distributed loads. These are all going to be automated loads for you. We'll see, while I also mentioned the semi-rigid wind loads, so the WL plus X, the WL minus X, all that's being shown here is 13 here. You can see the 13 and 6, that's the automated loads for you. Now, if you're going to be using this with our load combination generator, it's important here to turn on the generate semi-rigid diaphragm loads. So you can just say X and Z with the semi-rigid diaphragm loads, and it will automatically calculate those forces for you, those load combinations, to accommodate those semi-rigid numbers, these basic load cases here, these categories we've introduced. And then it will also, for the seismic, that one's pretty simple. You just make sure you turn on that reversible, and you'll have the X and Z. I'll also show this in an example when we get to the program too. So the modeling tips I'd like to point out, this one kind of seems a little obvious when we think about this, but our traditional theory here when we're using rigid diaphragms is only to model the lateral resisting system. So in this model here, I have 2 concrete walls. They're going to be our shear walls. I have 2 moment frames, and then I would just go ahead and I would apply my rigid diaphragms. I would apply this lateral load, and then the rigid diaphragms would distribute that load to the lateral resisting system as needed. So this is the concept we've been talking about up until now, and this seems like the way you would typically do it. So we would just do our lateral elements. We could leave our gravity elements back in Reso Floor, or if we were just doing a Risa 3D model, we would just not even address any of those gravity elements in the model, and that would work great for rigid diaphragms. But one of the things that does not work so great is when we talk about semi-rigid diaphragms. So once we say the same, almost exact same model here, let's go and put that model just using the lateral resisting system. So using those moment frames and those shear walls, and then drop in these plates into our system and let the loads go directly into those plate system. And what happens is when you start applying those loads into that model, those lateral loads, so wind or seismic, there's not anything to keep that stable, that slab. So you actually, or that deck or whatever you're modeling over there, you put that lateral load directly into it without any vertical stability. So now that has some out of plane and in plane stiffness, but it's not fully rigid like we were talking about prior. So it's kind of, you end up seeing a model that looks like, spaghetti on our screen. So it's really important to say, hey, that's probably not the greatest method to model when you're using a semi-rigid diaphragm. So instead of that, so I have a big don't do that. What you want to do is model all the framing in your model. So if you're going to be using a semi-rigid diaphragm, you want to say, hey, let's put all of those frames in there. You can use pins to help distribute differently the forces versus maybe you're going to be for your moment frames. Obviously, those are going to be fixed end conditions. The other start of the system is going to be pinned, so it doesn't carry moment as well into the columns there. But you do need to model the vertical resisting system as well, not just the lateral resisting system, in order to get a model that looks a little bit more like this as we apply the loads into this. Now we can see that there's some deflection, but it's not going to actually, at least it'll hold itself up. And then as we apply those lateral loads, it starts to help distribute more accurately. Okay, so now let's jump into some models. So I'm going to first jump into Risa 3D. So hang on here. Let's see. So Risa 3D. I kind of built a model here. I'm going to get rid of my plates for a second just so we can take a look at what this model is without the plates. So I will turn off my plates and I will turn off my nodes so we can see a little bit better. So I just built a wood walls. You could have done any type of structure to do this, but it was just kind of a nice easy model with wood shear walls. I have one masonry wall here on my outer wall, and I modeled all the walls in the system. So as I mentioned just now, I didn't call some walls gravity and some walls shear. That in wood, that is very common to just say model all the walls, and they all carry some level of contribution here for the lateral system, depending on where they are in the model. And so you can see that I have my model laid out like that. Now, prior to coming in, I went ahead and I created a material, a general material called general wood. I gave it some level of stiffness, kind of a less than what I see in other materials. And I said its density there. And I laid out plates on my model. So just to kind of give you an idea of how many plates in this model, it's almost 6,000 plates in my model. So there's a lot of plates. I play them out trying to be about 1 foot on center. So let's go ahead and turn those plates on for a second just so you can see. And if we look down on the structure, this is the side view there. If we look down on the structure, you can see I laid out these plates and they are already on my structure kind of submeshed to hit my walls and to hit different elements that are important in this model. So you can do that quickly by drawing plates and submeshing. I didn't want to waste our time today. I just really wanted to jump to that, but that does take a little bit of time. So, but you'd want to draw in maybe using your auto mesh or doing your draw plates and then submeshing yourself. So one thing we do here, so now once we've got our plates, I'm going to turn my nodes back on so we can see for a second. I did also turn on my diaphragm. So I put a rigid diaphragm in this model. The reason I put a rigid diaphragm in this model was so that I could use my automatic wind load and seismic load generators. Those in Risa 3D require you to have a rigid diaphragm. So by doing that, it gives me the values that I'm looking for, this force in the X and the force in the Z direction. So if we look at the wind loads here, I have 6.24 kips in the Z direction and 6.991 kips in the X direction. And that's my starting point for the amount of force I want to be applied into my model using my semi-rigid diaphragm. Now, I also see that I have that if I go to insert seismic loads. I laid out some of my parameters here, and then I could find my forces in the X and the Z direction. And those X and Z directions are also here. Just these are actually equal, but we can see those 2 foot values I'm going to be applying to my structure, and Risa did all the work for me based on a rigid diaphragm. So I'm going to jump back to the wind load for a second. Now, what I mentioned is for wind loads, we're going to want to apply those as distributed loads to the diaphragm. Unfortunately, the diaphragm is really just a semi-rigid diaphragm is just nodes, right? It's just a plate with nodes. It doesn't have distributed load method. But what you can do is just grab this number, the X and the Z direction, and you can calculate based on how much kips you want there. Actually, I'm going to go and look to the windward value, actually. Instead of the force, I'm going to jump back to one step below before that, which is my windward pressure. So I'm going to take 0.01, and I'm going to times that by the height of my structure that I need to, and then the distance between that I want to apply it to. So I'm going to say calculate that distance. I'm going to apply it to this face here, and that's going to be looks like 86 feet across this face. And I'm going to find that the value I need to apply per node that I want to apply to. So I have a number of nodes I want to apply at the face. That would come out to be about 47 pounds per node there. So what I'll do is I have actually, before I came into this model, I have some selected states already stored for me. So I'm going to grab this selection state called WLX, retrieve it, and I want to apply those nodes to a node. Each one of these nodes, I'm going to be applying a point load or a node load, and that will be distributed into the diaphragm and calculated based on those windward and leeward values. So the windward value is the first one I'm going to tackle. So I'm going to turn off this back one here and just apply windward in the X direction. So positive X, I can say let's apply some node or joint loads. And I'm going to apply that joint load to I already started a load combination called wind load plus X. And I'm going to say it's in the X direction. And then I'm actually in kip, so I'm going to say 0.047. And I'm going to say applied to all selected joints. So then it applies that directly to the structure. And this is my windward force. And now the other option here, I'm going to go ahead and unselect all and go back to my selection states. Go to my WLX, and now I already have those. Now I'm going to go ahead and unselect those, and then I'm going to put my leeward forces in here. So I go ahead and go into the WL plus X, the same exact combination. This leeward is a little smaller, so it's 28. Oops. And I apply that to the structure, say apply. And it gets dropped into that. Now, let me open up my basic load cases. So you can also review all of the loads that were in the fully rigid diaphragm right here. We list them out for you right on this spreadsheet. So you can see if they're not editable, they are then that light gray, so you can't edit them, but you can review them quickly, which is really nice. And then I can also see the ones I just added. I added 182 different point loads to my structure based on the windward and leeward of that. Now, the quickest way to create the other direction is just to grab a copy of these. So I will copy everything from this entire combination. I like to just highlight and say Control C and jump into the next one and then just Control V. Oops, we'll put the highlight over here, Control V. And now that means I got the exact same loads in one direction versus the other. But we know that's not the case. I actually need to do is just make those the opposite direction. So I'm going to go ahead and I'm going to say math on the block. I'm going to multiply it by -1. Oops, sorry. I'm going to multiply that one more time here. So math on the block, and I'm going to multiply that by -1. There we go. And we can see here now, so if we look back at our structure and turn everything back on, I have loads in each direction, and I see that they got just different directional. So now I'm seeing that I have everything turned in two directions. I'm going to do the same thing in the other way. So I'm going to say one more time, I'm going to unselect everything, go to my selection state. So if I recall my selection state in the X direction, or excuse me, the Z direction, and I'm going to jump to this one right here. And now I'm going to apply it to this face. So going in the Z direction this way, I'm going to be actually applying it in the Z positive direction. So I'm going to unselect any of these sides here that are going to go in the leeward direction. So this is windward, and we can see these are windward faces. This is a leeward face. There we go. And I can apply all of those loads here directly to our model. And this one is just a slightly different number. I'm going to say 49, and I'm going to switch this to the Z positive, and I'm going to say apply to all selected. And then I'll go ahead and I'm going to unselect everything, go back to my selection states, and you can see here, selection states are really handy for this. If you ever not used that before, you can just save anything you're looking at on your screen. It's a really helpful way to collect different loads and collect different views if you want to jump back to them and apply different things at the same time. So I got that. And what I'll do this time here, I'm going to actually go ahead and say copy. So I'm going to click on this and say copy this 25 into 26. This is another method for copying your loads from one version to one basic load case to another basic load case. And we'll go ahead and we'll just do math on the block. And we can multiply this by -1. Okay. So roughly, I'm just showing you a way to get these loads. I don't want to be get too much into the loading actual numbers there, but I want to show you how to do that. So we've got ourselves some basic load cases with semi-rigid, wind loads plus X, and then wind loads plus Z, and the negative and positive there. Next thing to do is the earthquake. So we mentioned here that we have the earthquake loads. If we go back to the insert seismic load, we need to accomplish getting about 6.45 into kips in each direction into this entire model. The fastest and quickest way to do this, and it doesn't really, it's just easy. We had the way we do it automated is going to be slightly different, a little bit more accurate, but this is the very quick and easy way to do it is just to take that entire 6.5 kips roughly and dump it into the entire model based on a surface load. So, and I can do that quickly by jumping. Let me jump up to there so we're looking at this view. And I can do that using my surface loads. So I say, let me pick out the basic load case of semi-rigid in the ELX view. And I can say this is in the ELX. And what I'm going to do is that's going to be roughly 0.001179. This is kind of roughly kips per square foot. I'm in kips, so it's pretty high. And I'm going to apply that to the entire plate system. Say apply, and I see that then it goes into that structure. Now, I'm going to zoom in a little bit so you can see that. So I now applied that in the X direction to every plate in my model. My plates are actually relatively similar size, so this kind of works out well for me. And things are relatively uniform in this model. If there was other issues there, you kind of have to get into a little bit more advanced of your modeling there. But for this type of model, it's pretty simple. I can do the same thing. I'm going to go ahead and do that one more time in the X and the Z direction. Really easy to just switch to the semi-rigid Z and change the direction and say apply to all selected. And then we see that now, as I zoom in, I get loads in that direction and that Z direction. So I've got my load combination, my basic load cases listed here for the two types. But what you'll notice is I still have those those rigid diaphragms listed as well as my semi-rigid. So a big mistake would be just to run the model now because I'd have doubled up loads. So what I need to do is take those diaphragms out of play, those rigid diaphragms. So I'm going to inactivate that rigid diaphragm. And it doesn't quite go away right away. So what I like to do is just jump into the insert wind load, and it tells me, hey, you don't have a diaphragm, so we're not going to be able to get you those loads. And that means they cleared out, which is what I wanted to have happen. The same thing I'm going to do is say insert seismic load, and then it says, hey, there's no diaphragm to find. So I then take it off. So in Risa 3D, whenever it's talking about a diaphragm, what it's talking about is a rigid diaphragm. This idea of semi-rigid diaphragms is something that we put in here manually. So I'm going to go ahead and say ELX in here and ELZ for this. Now I'm going to use the categories that I have. These will allow me to quickly use my load combination generator. A way easier way to jump into these loads because loading can get pretty complex once you get all these different directions. So I'm going to go ahead and say this is the negative X direction. And then I go to the WL plus Z and WL minus Z. Okay. There we go. So we have plus Z and all of the different combinations. The last step before you're kind of finished with this is that you now need to create those load combinations. So jumping into the load combination generator, I'm going to go ahead and just create a wind combination here. So X and Z. And then the big piece here is to make sure you check the semi-rigid diaphragm loads. You can say it's reversible. That really doesn't matter for wind, but it does make a difference for seismic. So we can go ahead and say X and Z and reversible for seismic and then generate those. So then we get a variety of different load combinations for us. So ELX in the two directions, and then we can go ahead and run the model. So it'll take just a second. I'm going to take those loads off her, and we're going to run this as a batch solution. If you're not familiar with the batch solution in the envelope, this is newer in the last couple of years. What we did was we added the ability for you to run not only just a single combination, which is a collection of those, which would be the batch solution, but also we would envelope all the forces for you. And in a model like this, it's going to take us just a few minutes to run this model. So it would be really beneficial for you to be able to get the minimum and the maximums out of an envelope solution, and then also be able to drill down and get the single combinations where you need to do more of the design information, like looking at a shear wall. You really need to know more things like what's happening on a single combination. So the fact that you can run all those at the same time is really, really helpful. One of the things we also mentioned is there's 6,000 plates here. So besides those walls being submeshed, we also added 6,000 plates to this model. So it's a lot that's being run behind the scenes. So you definitely have, you can see it's plugging and chugging, and it's going to be carrying all those loads through the structure, and it's doing a p-delta analysis. So this is a rather small model, one floor, but you can see how that can grow on you as you do the semi-rigid. So it's important that you need to do the semi-rigid in order to do it. Okay, so once we have our forces here, obviously what we're doing this whole model for is in order to understand the seismic and the lateral and the wind system. So you want to look at, you would then at this point, if we were working on this model for any other reason, would be going into our masonry results, we would be going into the walls, finding out what's going on in those walls, and all of that would be very important to us. But what I want to focus a little bit more on is what's happening in that diaphragm, that semi-rigid diaphragm. So I always like to do is look at the deflection. I quickly jump into the deflection, and I can see here the different deflections. So if we look at just seismic weight, obviously that's pretty easy, but if we look a little bit farther than that, we can see we have a lot of different types of deflections, and my nodes are kind of big in this model, so I'm going to take the nodes out. There we go. So you can see that the members actually deflecting inside there. There's going to be a little bit of weight in that. So you're not getting just a completely rigid element there like we saw more in a rigid diaphragm. We're seeing that the actual diaphragm is deflecting as it's being applied laterally. The other piece you can do, so you have an ability to kind of toggle through and see the different load combinations. You might want to pop open those load combinations beside that so you can see which one is the governing. You can also take a look at the plate forces. You have all that information here it's in an envelope, as I mentioned, as well as if you click that again, you'll get the plates per combination. So you have the two different outputs for yourself. But what's really important for me, I always like to look at is the contours. Beyond deflection, that was number one, right? You want to make sure you look at the deflection. Again, deflection is so important because if things are flying off your screen, it's your check there to understand whether it actually worked or not. If you don't go to that deflection, that's, you're basically cheating yourself out of the result. So you definitely want to start there. The next piece I always do is jump to the color fill panel plates there, and I look at my contours. So this helps you look at a contour of what's happening on the structure. So you can see this is going to be showing us directly inside of these plates how the flow of the forces are acting. So you can take a look. There's a index here telling us what the plate forces are, and we can toggle between the different load combinations to see where we find the worst case. We can see little stresses over there as we scroll down. It takes just a second to render it as we kind of pop through them. But you can see different things happening and what's happening as we display different things. So that was your MX, and you can look at your MY. These are going to be local plate contours that we're looking at here. This is plate by plate that we're seeing here. So you can kind of see all that different information, and that's where you'd end up kind of working with that diaphragm. If you had to design this diaphragm, this is where I'd end up looking at the contours, maybe look at our internal force summation tool, play around with different things inside of here. Okay, so now I want to show you how Reso Floor works and how that automates this whole process a little bit for you. So I'm going to close out of this, and I'm going to shut down Reso 3D for a sec. Hang on. Okay, so close that down and save that. And we'll jump back into Reso Floor. Oops, let's see, sorry. Reso Floor. Okay, so in Risa Floor, I have a model, a similar type model. In Risa Floor, what I mentioned is automated is going to be actually our Risa Floor ES, which is going to be your concrete floor slabs. So as I open up Risa Floor, just taking a second here, I'm going to open my concrete building up. And this is going to be my semi-rigid diaphragm that's automated in Risa Floor ES. You've got ES is going to be stand for that concrete floor level that we can do design on your concrete floors. When you first start a model, you have the option to do a concrete floor, a concrete slab, or you can do a beam supported slab. So for the semi-rigid diaphragms, they are going to be automated through the concrete slab element there. So what you see on our screen, if we just take a quick look, this is a concrete floor that has design. So reinforcements all shown on my screen, a two-way slab. I'm going to turn that off for a sec. I'm going to show you what it looks like here. It's just a slab with that green outline is a slab design. We've got some shear walls, and as I mentioned, you're going to make sure that you place all of your columns as lateral columns. That just means that they're going to go over to Risa 3D and help support that semi-rigid diaphragm when we get there. So we've got some lateral elements in this model. This is just 2 stories, and Risa Floor carried all the gravity loads down the structure. It went and designed all those gravity loads. It designed the reinforcement for that slab, and all you had to do in here was tell the program that you wanted to use for that slab design. You can lay out all your slab information, but for the slab design, we were going to use the semi-rigid diaphragm. You had the option between a semi-rigid and a rigid diaphragm. And in this model, I used a semi-rigid diaphragm in order to use that semi-rigid diaphragm tool when we get over to Risa 3D. I also mentioned that, and this is for rigid, semi-rigid, or flexible, it's important to note that dynamic loading there, that dynamic mass is coming right off this column off our uniform area loads. So if you're not familiar with Reso Floor, this is going to be a floor plan, and that floor plan assumes some uniform area loads. That the dynamic mass comes right off of this dyne load. I also placed some extra loading on this model. So if we jump in here, I'm just going to quickly take a look here. I applied some dynamic mass to this structure that's a little different. Let me turn off that reinforcement so we can see it. I just kind of said, hey, maybe we have some equipment in this area that's going to apply some extra dynamic mass. So maybe 2-point loads and some line loads. Above and beyond our standard uniform load, we have some additional dynamic mass. So that's a little different for what's going to happen when we get to the seismic calculations in a semi-rigid diaphragm. So in order to get this model over to Risa 3D, from Risa Floor, we just go up to the director button and use the Risa 3D director. And the same information comes around. So as I mentioned, this screen will always be there for you. So you can see you plug in all the information for the actual location, and it gets that forces in the X and forces in the Z direction per floor level. So this model has 2 floors, and we're seeing that's going to be the wind loads per floor level. Then we say OK, and we see the same information here in the seismic. So I put in some information on the site. So I have 0.16 and I have 2.7 there. So this is real information from a site location, and then I have the different forces in the X and the forces in the Z direction. So I can say OK, pop out of there, and now I have my model in Risa 3D. What you'll notice happened right away is that I got a diaphragm edge. It's a slightly different color than you're used to if you're looking at the rigid diaphragms. This is going to be a little greenish color, and that indicates that it's our semi-rigid diaphragm. And this is our semi-rigid diaphragm right now, just gives us the outer perimeter of that diaphragm. When we come over from Risa Floor, all the loading comes across with it. So you'll see the dead load is listed on that diaphragm, on that slab. The live load is listed on the slab. And then as I scroll down, the wind load in the X direction. So what happens here in the wind load in the X direction? Let me double show you that. So wind load in the X direction and Z direction, those are going to be based on that rigid diaphragm. When we were using the semi-rigid, we're down here in the semi-rigid wind loads and X load. So this is all automated for us. Remember, in the last model, we applied these. But this model, this is all done for us. So we can just review that. And we see here on each floor level, you're seeing the windward and the leeward forces. What's nice is that curved element there, that actual, where we said it was a little change, it's not quite directly on per point when we did it ourselves manually, it's all calculated for us. So whatever needs to be on that distributed edge there is put on there for us and calculated for the windward and leeward directions. And we can see that in the Z direction as well. So Z is pretty easy there, but we do have this long diagonal edge where we'd have to calculate that on that projection. So it's a little harder, but it's all done for you automatically. And we also have that earthquake load. So if we jump back to the ELX, now that earthquake load, we saw it lumped in per each column. We see there's a surface load that's being applied. We also can zoom in a bit, and we see that now whenever we had that equipment load, that dynamic mass, it also turned that value directly into a lateral load in the X or the Z direction. So that's pretty simple here. Just automatically does that for you. If you call it a dynamic load, dynamic mass load, then it will automatically put it into that for you. So you can zoom out a bit, and you can see here. So all those loads directly are in your model based on that. So there's no toggling of the categories or anything like that for you. It's there. We can then go ahead into our load combination spreadsheet. And I see that we already have here my different load combinations. If you forgot from the last one, all we did here is I used the wind, X and Z using that semi-rigid diaphragm. That turned on, and it is important just to point that out again. This is probably one of the biggest user mistakes is the category there, WL plus X. That shows this WL plus X right here is that semi-rigid. Those are the values that are going to be applied. Sometimes users try to use just WL, and that would mean that it would be something we did not apply to our structure. So I didn't use a WL in my category. So it's really important that these match. When you're using that category, you use it in the load combination. And so this model is actually solved for us. So I'm not going to run it again. I want to just make sure it's already solved so we can just take a look at the design results. Once the forces of, I ran a batch solution prior, so you can see that I've got all the design results in this structure. Again, if you were working on this for your lateral resisting system, you would end up taking a look at the wall forces and the wall designs. So looking in to see that you've got enough adequate resistance here for your lateral design and your concrete walls. You might look at those columns, make sure nothing is going to be, we could do a biaxial stress on those columns, make sure that there's nothing happening in each one of those columns if there is a problem. But the slab itself is also really important to review. So I'm going to go ahead and just isolate the top one diaphragm up here. So I can go ahead and unselect this lower diaphragm and just look at the top diaphragm. I'm just going to lock it. So I'm just looking at that one top diaphragm. And I can turn the diaphragm forces on. These contours are going to be global, a little different. So there are plates inside of there. Let's take a look at that plates before we move past that. So there are plates just like we did in the Risa 3D on its own. But you'll notice it's all submeshed, done for you automatically to the locations, the control points that you need, the column tops, all that is already submeshed for you. And so that's happening behind the scenes. But what you can look at is the contours. And you can see here, under these contours, we have a global direction MX and MZ. So this will help you do, if you were going to actually do reinforcement for lateral design, you could do it this way by looking at this. Probably that's less common, but you could, if you needed to, look at the stresses in the moments. We can flip between different categories. So obviously we want to, that's as the category, the load combinations that govern, we would want to flip through and make sure that we are finding the maximums for that. I can jump to MX, and so this is a two-way slab. So I see that classic two-way slab directional loading where I'm seeing the moments distributed there in the two directions. And then I can say, okay, and now the other piece I can do is, so if I do want to do design on this model here, I'm going to look at this in a plan view. If for any reason I wanted to do design in Risa 3D on the slab, I can use what we have. Let me turn off my contours for a second. I can use my slab internal force summation tool, and it turns my whole mesh on automatically. And then I can click on any point in the slab. So I'm clicking on a grid intersection here to find this force and moment inside the slab. So using the cuts here, I'm going to cut across, and this is just kind of mimicking what the internal force summation looks like with a design cut. So I can also go across anywhere. I could draw it across the entire slab and see forces across that entire slab on one side or the other. But it is very useful to be able to click a localized area, so more point to point, and find that value there. So I'll show you the wall one. The wall can get you, look on the wall, you see all the different forces in that internal force summation tool. It tells us the different forces, the moments, the geographic center of the items, and so it tells us what's happening, and you can do reinforcement design based on that as well. So you've got the contours here. I'm going to show that contour quickly too. If we look at our contours one more time, I'm going to show that there. So you have a lot of different abilities to see, as well as going into stresses. So probably not so important, but you could drill it down into all the von Mises and all information for you. But typically we're going to stay more in the actual forces and the moments. I'm going to say okay.